Bhushan sir, I am audible to you?
Yes, you are audible.
Okay. Our
Dr. Mukherjee, should we start?
yes, sir, we can start with if our speaker has already joined. So only one thing that we have attendees like 4.
I think there are a lot of other participants. Anyway, so I think we should not waste time. Okay. Okay.
Yes, we can start.
Okay. 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 Okay, no issue. So, okay. So, yeah. So, good evening to all the participants and all the students of the student chapters. And especially we are very much thankful to the institute. I think it is Dr. Mukherjee.
Yes, sir.
It is this. My voice is repeating here. I can hear. If anyone just switch off your mute your system.
Okay. I request all the participants to keep their system to be under mute condition. Let research speak. We'll just then start.
Okay. Now I think it's okay. Okay. So, yeah. Okay. So thank you very much. Thank you very much. Today actually we have assembled to discuss about the bio-inspired flapping wing mechanism, which is a great challenge for us nowadays. And we are having with us the very great person, Dr. Bhushan Dewang, who is from the Central Mechanical Engineering Research Institute at Durgapur, from say CSIL lab. And I think that this webinar will definitely give us some ideas about various application of this particular technology in the area of mechanical, as well as some kind of aerodynamics or aerospace engineering also, and a lot of other case studies and application things will be discussed by our panelists. And I'll not waste my time. I'll hand over to Dr. Mukherjee. You just start your moderation so that the other participants, they can be well aware about the topic. Thank you. Over to Dr. Mukherjee, please.
Thank you, sir, for the introduction. The IEI do not require any introduction to us. We all are aware of the Institution of Engineers. It has been like century for serving the nation with various scientific programs with 3 lakhs plus corporate partners and 124 centers all around in India. IEI has scaled only heights. So I will just take this opportunity to thank the IEI for supporting this, and also I will thank our today's panel discussion panelist, Dr. Bhushan Dewangan. I will just share with you some small introduction for him. He is actually a project scientist on the Human Centered Robotics and Cybernetics Group, CSIR, CMERI Durgapur. He has completed his PhD from NIT Roorkela. His experience publishing more than many reputed journal papers, and his research work widely focused on bio-inspired flapping wing mechanisms. Recently, he is working in various robotics projects and has shown exemplary research work in his aptitude. So, I will. It's a very honorable honor to have him as a panelist today from CSIR CMERI Durgapur. I'm. It's over to him for his lecture.
Thank you, Dr. Shubham Mukherjee. It was a nice introduction of me. I would like to transfer my thank to Institution of Engineers and the University Institute of UES. So my topic will cover what are the challenges we are just facing for bio-inspired flapping wing mechanism. So I will just share my PPT here. Dr. Mukherjee, my slides are visible. Hello.
Yes,
Hello.
sir. Your slide is visible.
Okay, thank you. Thank you for acknowledging. Okay, thank you. So I will tell you about what are the challenges we are facing in order to manufacture, whether we are doing any analytical part, simulation, all these things. So I will cover in this lecture session. I thank to IEI Technical Sessions and Institution of Engineers, India, which is organized by Students Chapter of IEI. So, introduction. So, why we need such kind of mechanism? Basically, these are mechanism means are generally being referred from some bio-inspired or means any birds or any animals. Why we are just bio-inspiring means we are just get confidence from by watching or by seeing the birds. They are flying uh, flying very effortlessly without any uh, entangle in the cluttered environment they are fly. So all these things, whether if you take any example of the human-made architectures, we always refer to our natural creatures, how they survived so much billion years and now they have evolved so much that their uh, dynamics we are studying, and we just want to get efficient thing from that so that we can make our society and our life better. So in bio-inspired things, basically if we are talking about the major issue is that the application purpose means what we need for this means if unmanned vehicle or any type of instrument or machines we have to make. So what is the application and why we want to use that? So that questions always come in our mind. So in order to just reduce the effort of human being, as well as there is a scarcity of fuels and energy day by day we are facing very pollution like this. So we have limited resources, and limited resources, using that limited resources we have to just optimize for ourselves so that our applications can be fulfilled here. So I'll just go to the why the unmanned air vehicles are generally used, and they are being inspired from nature. So in this, the unmanned vehicles are being classified on different types based on their wing type, their weight, their range. So in the flapping wing, our wing just flap with respect to fuselage, means body of its own body. So if we consider and characterize based on the wings, so we have three types. Okay, so fixed wing UAV, rotary type UAV, and flapping wing UAV. In fixed type UAV, in the practical example, you can see that it is a Skywalker fixed wing UAV. It is a kind of a small prototype. So if you take any unmanned air vehicles, means there is no operator is sitting inside it and it is working freely with the use of some remote operation or some kind of communication between the operator or the uh, vehicle. So the the big example you can take for the fixed wing vehicle is that airplane. Okay, here the wings are attached to the fuselage. Here they consume very much amount of fuel because they need runway, they need time to get take off, and I know it is a very means developed kind of technology, but still we are just facing so much of issues of fuel consumption, pollution is also there. So what is the means efficient way to just reduce the pollution as well as the fuel consumption? So for that we are just again we have a type, a rotary wing type. You have seen helicopters. So helicopters is also a type of a rotary wing. Here in the single wing rotor type we have, and the multi-rotor type you have seen the different motor multi-rotor. You have seen the drones. In the different application, you might have seen the different Zomato or Swiggy. They are just planning to launch their operations in order to deliver their products from their source plant to the consumer within a stipulated time. So some work is still is going on, but most of the work has to be carried out in very proper way, and it has to be means rigorously. We have to experiment. And third type is a flapping wing UAV. So here the wings are just flapping with respect to the fuselage. The body, with respect to this body, the wings are flapping. So this is the kind of flapping wing UAV I will just talk about here in this lecture. So we are having two types. One is ornithopter and another is entomopter. So in entomopter, what happens? It mimics the insect flying capabilities. And here in ornithopter, we just mimic the flying capabilities of birds and birds like features. So this is a classification on the UAV based on the wing type. So conventional UAVs that are fixed in a rotary wing face limitations at low Reynolds number. So limited maneuverability and agility in cluttered environment. So high energy consumption during hover and low speed flight is there. And they are also having high acoustic signature and detectability. So these are the limitations, and due to these limitations only, we are just focusing on the flapping wing UAV. Then why we are using the flapping wing UAV? So bio-inspired flight systems offer a promising pathway to overcome these limitations. So ornithopter, it mimics the bird flight. It is very high efficient. it generates lift and thrust simultaneously when it flaps from top dead center to bottom dead center to top dead center. A complete flapping cycle it happens. So overall lift and thrust generation simultaneously happen, and this means flapping cycle makes the UAV to move further and very efficiently. So better performance at low Reynolds number and capable of hovering and agile maneuvers and reduce acoustic signatures. As compared to fixed and a rotary wing, it has reduced acoustic signatures. Because of this mechanism and because of its structure, rather I say, it is very much suitable to reduce the different acoustic signature, and also it can reduce the cross-section area if this UAVs can be used for different multiple applications, military and civil applications. So there also they need some kind of UAVs which are undetectable by the foreign threats. So like that, this UAVs are very much promising and can be used for different applications, especially for military applications. So, and also it can be used in the civil applications where recently we had unfortunately earthquake in countries. So in that also we can use this kind of UAVs. So it is very beneficial for our human society and like that. So I will just explain why ornithopter. I've already explained all these points. So here I have just mentioned this, the Festo. Festo is a company which has made SmartBird in 2011. So it is a flapping wing unmanned air vehicle developed by Festo. So here I have numbered. The first is the flapping wing. Here you can see there is a flapping wing. It's a foldable flapping wing, you can say. And this is the two is the fuselage, that is the body, that which hold the whole mechanism or heart of this machine, this prototype, battery, all the mechanism storage and structural stability will be comes under to handle all the thrust and lift. And third is the tail. Tail always be used for the roll and the pitch thing, so that it can move in the cluttered environment very smoothly without any problem. And fourth is the nose one. So this is the nose of the ornithopter, and it is very much essential if you are going in an environment and you want some efficient flight, because you can also take the example of the bullet train. How bullet train just look from front, how they have made. They have also mimicked from the bird shape, how its fuselage and how its nose look like. So based on that and the different iteration, different simulation they have done, and they finally found out what is the problem and how they achieve all this kind of speed. So this is all, if you want to make the whole thing happen, so you have to focus on all those four things. So why it is challenge to make such kind of mechanism? Because wing kinematics is very complex. Because we have to replicate the natural flapping, twisting, and folding motion accurately at the instant whenever we require that. So right now it is a challenging, but in future I definitely know that we will overcome this limitation. And second, the aerodynamic complexity, because it will work in unsteady airflow, and whenever this flapping happens, vortex generation happens. And this vortex generation, sometimes it's very useful and sometimes it is but useful. So for that, we have to just compromise this the complexities, and we will be working on the low Reynolds number aerodynamics, and which is very difficult to model. And still, the research fraternity has done a lot of research on it. They are achieving good results. And third is the structural flexibility. So I was talking about the structures, and it's if it is flexible only, then it can balance the wing compliance with a sufficient stiffness for efficient fit. Means what they are saying means wing compliance with a sufficient stiffness. So wing should be have sufficient structure flexibility. Otherwise, if it is rigid, it might break in between the operation or in between its function. So all this thing we have to just see whether this will work or not, kind of thing. And power and energy efficiency, achieving long endurance with lightweight energy sources. This is the major issue right now we are facing, because in lightweight energy sources, the weight of the battery itself, it goes around 200 to 300, more than that 3 to 400 grams. And for if you have a lightweight energy source, then only you can achieve the long endurance. Means long range you can go like that. So it is also a challenge. And the lightweight mechanism design, it is also means minimizing the weight while maintaining the structural integrity and reliability. As I talked in the third point, the structural flexibility. So we have to just optimize kind of thing we have to do. And the another important point, that is actuation challenges. How we will develop such a high frequency and compact and high efficient actuator that can mimic the biological motion, which will work in the cluttered environment. So this is a very important point. Then flight stability and control. It is another topic, because controlling and stability and have a stabilized system. It is another thing. So in coordinating the flapping, steering, and maneuvering under the disturbance, many research are being studied on this disturbance. Means how this UAV will react when we are given some kind of a disturbance, air disturbance, or some kind of pressure differences we have made, or we are facing very large amount of velocity of airs we are going through. So all these things we can do in a controlled environment like our wind tunnel. So in wind tunnel also we have some limitations. So still we have to just check how that thing will work. According to that, we have to just replicate the things how we want to just get the technical jargons of that prototype. So all these things we have to just look at. Manufacturing constraints, it is a thing, because fabricating intricate wire-spine structures with precision and durability is a must. So we have to look on that also. And the material fatigue, because flapping cycle, it will work continuously. So there is a chances that it will wear, and it will wear way before as we have expected, according to our factor of safety. So reduce lifespan, it can happen. So like that also, we have to just check whether this material fatigue, all this thing, we have to just optimize thing, and we have to just carefully take all the things and do it in a simple, in a compact thing if you want to model this mechanism based UAVs. And the real-time sensing and control, integrating the lightweight sensors and adaptive control algorithm for autonomous flight. Like this. So I will just share my some slides where I will just tell you that how mechanism is being analyzed and how we can say that this mechanism can work. So I'm just sharing, this is my PhD work. So this is the flapping foldable wing mechanism. So we have a patented flapping foldable wing mechanism. And it was done by Dave. And my supervisor also put this. So we'll just, I'll just show you how we did this. So here you can say this is the modeling we have done in CATIA. And this is a 3D model of the flapping wing unmanned vehicle developed by Pradhan et al., as I was discussed before. So in this, what we are doing, here you can see this is a mechanism. And this is the heart of this whole prototype. So if this fails, then whole prototype will fail. So for that, I just use with my supervisor MSc Adams, which is a multi-body dynamic software, where you can find out the kinematics and dynamics, the different forces at the joint. You have to find out how the link will react, if the link is flexible or is it a rigid, how they will react with each other. So like that we have done, and I have just shown here some isometric view, side view, and top view. So here in the mechanism, I will just tell you brief about it. So this is the foldable flapping wing mechanism for a bio-inspired UAV. I took this, and in this mechanism, I just break this into 3 parts. So in 3 part is that this crank slotted lever mechanism. So here you can see this crank is rotating, and this slotter is moving through this slider. So this is, I think that all the audiences are from mechanical. So this is the 4-bar mechanism, a kind of inversion of the 4-bar mechanism. So if we give one input, we will get the one output. Like that, we will just using this concept. So here, this crank rotation means we are just rotating through some DC motor. Okay. So if you want to check whether this linkage kinematics is what we are expecting, means how it will flap, at what velocity, and how will be the acceleration when I give this crank rotation about 100 RPM or 200 RPM, like that. If you want to optimize this also, how this will, the link weight will affect the whole mechanism. So like that, we have to just see the whole system into simpler one, and that simpler one has to be modified such like that we just simulate in the software as well as with the mathematics. So I've done similarly like that only. I've done in using the analytical methods, and I just validated with the MSc Adams simulation. So here you can see the crank slotted lever mechanism. Again, this motion of this slotted lever will try to move this this shaft, which is again attached to a small spur gear. Okay, so that small spur gear again try to rotate this big spur gear, and this is big spur gear is again attached to the rectangular shaped fashion bevel gears. So this mechanism I'm just using in order to get the reverse motion. If I'm giving the clockwise to this slotter, here my whole mechanism, if this annular ring, which is can attach to the opposite bevel gear. So it will give me anti-clockwise motion, but the orientation will be the same degree. But its orientation is means it will rotate clockwise. If I am saying this slaughter is rotating clockwise, then this annular ring, red, you can see it providing me then anti-clockwise like that. If it is clockwise, it will give counterclockwise like that. And this proper mechanism will give boost to this linkage. And this is also a special type of 4-bar mechanism. Here I am using the special type of 4-bar mechanism because this link looks like a 4-bar mechanism, but it is actually a 5-bar mechanism. Because in the fifth link, we are just assuming that fifth link is assumed to be 0. And we are just replicating the 2 input. The 1 input from this annular ring and another input is from this here. So this whole mechanism will give birth to the flapping motion. Rather, I would say that foldable flapping wing mechanism. We will just develop. So this is the kinematic analysis of crank sorted lever mechanism. So we have just done this in the mathematical modeling. So like that, you can say slider is over the slaughter, and that slider is connected to the crank, and crank and the slaughter are being ground. So you can see here the different length I have given. The angular orientation of the slotted lever, angular velocity and acceleration of the slotted lever are obtained like this. So basically what we have done, we have just used the geometric properties, and using this formula, we have just find out, and we have just differentiate with respect to time. We'll find out the angular velocity, and if we double differentiate with respect to time, we will find out the angular acceleration of this particular slaughter link. And here also our input is omega and theta, where omega 2 represents the crank. Here omega, how much RPM you want to have, that RPM you will just use that, implement that, and theta here will show that theta 2, that this crank is rotating from 0 to 360 degrees. So if you give this formula in the MATLAB or some kind of another analyzing software, and if you code it, you find out that it will give some plots that I will just explain you, that it will work very good. Similarly, this is the gear mechanism I was talking about. So this is the left wing side. This is the right wing side. These are the annular ring. These are the annular ring which are just attached to the lower bevel gear, and these bevel gear arrangements are in rectangular fashion. And in between them, the shaft is there in order to hold these bevel gears. And you can see here, this is the annular gears, and the sector gear, sorry, this is the sector gears, and which is attached to it. So if we are just attaching the whole slaughter link, if the left wing, so it's the responsible of the sector gear to give the motion in the opposite direction to this sector here. So similarly, we will just use the concept like this, and we have done the kinematic analysis of a special type 4-bar mechanism. So similarly, we have just find out the whole equations, a bunch of equations, and it took time to understand what is happening, and it had been validated with the MC Adams. So this is a structure we have followed in order to do simulation in Adams. So in this, the whole how bodies are created. Bodies are created using CAD software. Any CAD software you can use. I here used CATIA because in CATIA you have many much options to do. So like that, and the connectors here just means what are the joints we have to make. Because if you make this link, there is no purpose of the link unless until you have properly connected. So how you will connect? You will connect using through joints. Okay. So here fixed joints, translation joints, and revolute joints we have used. So this revolute joint we have used in between the links where we want to have some restricted motion, and fixed joints like this base, which will be kept inside the fuselage. And this translation joint, you can by saying itself, you can see the slider inside the slaughter. This is the translation joint you can obtain. So in the motion, what I give the joint motion to one joint motion type. Here also you just focus. Here the translation joint motion and the rotational joint motion. Here I have crank, which is a rotational joint. Okay, so I will give only the initialize the input motion by selecting a joint which is rotary motion, means which is in the revolute joint, and I give this using with initial displacement and velocity, which is the function of time. Acceleration I will give 0. So and initial displacement I will give 0, and initial velocity I will give random value if you want to do like this. And for my PhD work, I have taken as 1 radian per second, 2 radian per second, and 3 radian per second, just like that, in order to find out the different aspects of analytical mathematical modeling we are doing, and MSc Adams and the simulation we are doing. So we are just checking whether this mechanism is functionality is working, can be used for the fabrication part, and can be used in the environment. So like that, sorry. So in that, we just find out and do the simulation. And here we just initialize and give the end time and the steps. And based on that, we have the started the simulation. And when you just start the simulation, it will give the plotting. So this plotting will come under the post processor. So like this, we just find out the different acceleration of the links, and velocity and velocity, and orientation, how they are reacting with each other. So this is the data I had taken it. And also, why have you can ask why I have only choose crank sorted lever. So I have used the crank sorted lever because it works on the quick return principle. So here what I need, that I need a longer forward stroke, and the return stroke should be in in less time. So like that I just used, and here I just used with some with the calculation and the dimension we have find out, and using that we find out that quick return ratio we have to use 2, and according to the link dimension. And here also you have to just see the condition of the Grashof chain, whether one of the link of the mechanism can complete a full rotation as compared to other. So like that, we have just targeted using the different mechanical aspects. And in previous study also, what we have done, we have just used this Grashof chain condition where the B plus C, here B plus C means the length of the different links in shortest link, and the sum of the smallest and the smallest and the longest link should be less than or equal to other summation of the length. So like that, we also discovered that I have not mentioned here. And we have done for this because we have to check whether the different link length dimension can be assumed to mechanism design. So like that, we just use such kind of conditions and such kind of condition. So this is the comparison between the analytical and the commercial software and the CROC have used. So here you can see the slaughter orientation of link 4. So here the link 4 is itself a slotted lever. So orientation, we are just comparing it with our mathematical modeling and with the commercial software. All the conditions are taken as same, and using that we just found out that our mathematical modeling is correct. So based on that, we have find out the orientation, angular velocity, and angular acceleration like that. So in the second module, I will just touch up, not fully explain that how this will work. The flapping foldable wing mechanism means dynamic analysis, how aerodynamics and DC motor selection will happen. In the trips in short, I will just tell you. So in dynamic modeling of various parts, starting from crank sorted lever mechanism, followed by gearbox assembly, and after a special type of 4-bar mechanism. So all this dynamic modeling I will be showing you, because before that we have just done kinematics, because it is a kind of a flow we have to just follow in order to whether your mechanism is stable, whether if you fabricate it and you want to do some experiment in the environment. So before that, we have to mathematically and simulation wise, we have to become very strong. And like that, we will just use when that if we have the wings, flapping wings, whether it of a rectangular type or quadrilateral wing type, how it will create the lift and the drag. So this kind of thing I've just used using ANSYS Workbench and just find out. And based on the values and thing, I just find out the DC motor, how DC motor selection will happen. So this is the dynamic set. I've just used the Newton-Euler proposition for each section, means each part means crank sorted lever. Then here in the crank sorted lever, each link will have some kind of force, and this force can be utilized like that. So similarly for the gear train arrangement also this will happen, and dynamic modeling will have for also a special type of 4-bar mechanism. So this thing you have to do if you want to have some stable and good thing you have to make, means prototype you have to make. So all these things you have to just try to consider. So in the computational fluid dynamics, I've used using the ANSYS Workbench. So CFD is a simulation-based approach that employs numerical algorithms to solve the fundamental equations governing fluid flow, such as the Navier-Stokes and continuity equations. So for executing such CFD-based simulation, we have to just apply the ANSYS Workbench with Fluent as a subsystem model and closely study the complex behavior of the structure, fluid, and this FSI means fluid structure interaction. How the fluid will interact with the structure when the whole environment is having an effect on it. So like this, the forces are obtained performing the surface integration using local pressure and viscous stresses. So these are the things I just used in my PhD thesis. So this is the rectangular plane form and the quarter elliptical plane form I just used, and I just compared which will be the very efficient one. So quad elliptical plane form was very efficient, as and I just use the ANSYS Fluent workflow like that. If anybody wants to do simulation, so here geometry, mesh, setup, solution, results like this. Here meshing, I've used the overset meshing using the boundary and moving domain. So like this, you have to set up the boundary conditions. Based on the boundary conditions only, that you initialize and calculate the results what you want to have, drag and lift, all this thing. And this is the flow chart I've just shown here, how the different subsystems in the CFD simulation works. So here it is the prediction or mathematical modeling I've done. So here we have to use UDF, user defined function, how this flapping is happening. This we have to just insert in the ANSYS using C code. It works on the C. So like that, I just find out and I just compared with the one paper. It shows good results. So here I just showing you how I use the overset mesh. So if you want to find out the flapping wing simulation, you have to use such kind of things. Overset zones, background component zones. This is the background zone, which is the big area, and inside that you will have a component zone. Where inside that, this rings can be placed, and we will just try to find out and do the simulation how it will react with each other and how the forces, if forces and drag forces. It also we can find out the pressure like that. So this is the independency test I have done. So this is the kinematic coefficients I have just validated. Again, I have validated because it is a very huge concern for us. So I just use that. You can see. And this estimation and the comparison of the aerodynamic load using the different wing shapes, as I was talking about that. This RW, the rectangular wing, and QEW is the quarter elliptical wing. So here you can see that your aerodynamic forces, which means your drag is very less in quarter elliptical wing, whereas in F8 and F5 just show the wing side. Means in wing we have two sections. That is a first, which is near to the shoulder, and which is away from the shoulder. It is 8. So like that, link 7 and link 8, we have just combined this into a one wing, you can say. So link 7 is the inner wing and outer wing is the link 8. Like that, we have just compared and we just found out that the F5 is the drag and FZ is the lift, and are identical flow conditions we have just used. And fair compression we have just made. And you can see the rectangular wing exhibits higher drag compared to the quarter elliptical wing. And whereas the quarter elliptical wing reduces induced drag and tip vortices, resulting in smoother flow and improved aerodynamic efficiency. So here also you can see this is lift comparison, and here you can see the dark one is the quarter elliptical wing, and it is more as compared to the rectangular. Here it is, you can see it is very much louder. So all this thing we have just find out comparison, and we can conclusion we can say the elliptical span-wise load distribution in quarter elliptical wing minimizes induced drag and lift generation efficiency. These are the dimensions we have taken, and these are the flow chart we have just used to show that we are just again giving some kind of load. So we just checking how much the load can be beared by a DC motor, so that can get designed by DC motor. So for the DC motor, we have to just find out how much torque we have to consider it. Output torque, output speed, electric gearbox ratio, supply voltage, all these things we have to consider in a flow chart. How will be the motor speed, all the gear efficiency, peak torque, how will be the mechanical power at output, what will the power at the motor shaft, all this consideration we have to take. Then after we will just find out that how we can have the selection of the brushless DC motor based on the above. So I have here taken brushless DC motor and I compared with it and this work fine. So in the second and the third part, I can just say if the time is there. Okay, I can go forward. Time is there. The foldable wing ornithopter, I can say this is also another dimension we have to look for, because if the wing is ready, then our whole focus will go to the fuselage, means how the body structure will be balanced out and how the whole thing can be kept inside some structure. So these structures has to be means very optimized for the environment it about to go. So for that we are just focusing on the fuselage design. So this study benchmark geometry and parameterization of these things. I just taken this all this thing referred using the 150 seat civil aircraft proposed by Rouhani and Zangarian 2022. So they have mentioned the 150 seat civil aircraft proposed, and according to that, they have just mentioned some fuselage based on that. So in their fuselage was about in meters, and their parameters were about 10. So I just find out that why can't we just optimize it for biospire ornithopter prototype. So I just used that concept and made the 8 parameters. Here in the nose section we have 3 parameters, and in this mid section, which store our electronic item, having 2 parameters. And similarly, we are having here 2 parameters in the tail bar. So we have just again add one flow parameter, that is our angle of attack. And this angle of attack we have just mentioned that it have some lower bound and upper bound, and using that reference value, we are reference value it being taken from a seagull. Why I've taken seagull? Because it is a real bird, and we have optimized its body shape based on then how they shore near the beaches or mountains ranges, because there the air means air velocity are very high. So their birds what do, they don't flap regularly there. They just keep their wings straight and according to the flow, and they just disregard the all disturbance flow, and they just use that soar kind of approach, so they can to get have some prey, so like that. So here I will just show you how I just use this approach and to find out the optimization basically I've done. So this is the reference value I have just taken, and this is the flow approach I have just taken. Where design motor I have used of the ANSYS thing, ANSYS workbench I have used machine. Then here I use ANSYS fluent, and so that I have just got the solution, and based on the different sample sizes and different test results, and just use the response surface optimization. So here I've just used and find out that this response surface optimization did great, and we just used the concept of design of experiments, then genetic aggregation response surface method, multi-objective optimization using non-dominated genetic sorting genetic algorithm. So here also I've just used some turbulence model because we have to just replicate the flow condition across the body. So we have here used SST-QMI turbulence model. So it is by default I think there in the axis. And we have just maintained the y plus value of 40 and the growth rate of 1.1 and the residual target of 10 per minus 4. So that accurate boundary layer resolution we will get and grid independency test verified using cross pose fine meshes. So here we did the grid independency test, coefficient of lift and put the number of elements, and like that we done the meshing. And consistent flow like that we just used how we will find out the results with pressure controls, velocity controls, strain lines, coefficient of rate, drag, and their ratio. Like this, we just done this. So in the future shape design, here we have just used the design of experiment, response of this method, and LHGA to optimization. So like this, we have just find out the diverse Pareto optimal set where we will get the optimal solutions, and based on that optimal solution where all solutions are optimal and according to our requirement we can choose any one of this, and using that I got my optimized. So I have here just taken S1223 airfoil because it provides very high lift as compared to another NASA airfoils. So S1223 airfoil provides high lift at low Reynolds number, which was developed by Salich and Global in 1997 in late 1990s. And it has relatively thick profile with maximum thickness of 12.1% and 19.8% for. And like this, we just using this because this is the important criteria. Means it is relatively insensitive to stall as well as better stall noising than other airfoils. This is the experimental present simulations. Experiment this have been done in other people. I just iterated with the simulation like that, and this is means how nose parameter RM1 are reacting with CL and CD, means how it is sensitive to this parameter. If you are increasing nose radius and how CL and CD will respond. So like this, I just conclude with that this sensitive study of a different design parameter based on the lift coefficient, you can see the most sensitive to the parameter is RT. Okay, so RT means radius of the tail part, and alpha is angle of attack. So this angle of attack is very essential, and we have to just look how this are getting. So we have to just focus on this RT and alpha values carefully in order to have efficient lift and less drag. And this is the optimization result we have find out. And here we have used population 200, crossover 0.98 and mutation 0.01. And here I just use the maximized lift and the minimized drag for fuselage design. So here I just generated the Pareto front, which represents the trade-off between CL and CD. And this final fuselage shape selected from the Pareto optimal set. So like that, this was the optimum fuselage. Benchmark geometry we have just made, and using that we find out the optimum geometry. And this is a comparison of the aerodynamic coefficient and their improvement. So you can say the CL is coefficient of lift and coefficient of drag. Here you can see the improvement as we have just optimized it. So CL by CD also we can see the improvement are very large. So our optimization is correct and can be used further. So like that, an analysis based on flow physics. Here you can see the pressure contour. So in the pressure contour also you can just and with the optimum you can see the different results. Here the pressure are very less as compared to before because the pressure is very large. So using this you can see light little bit of light gray and blue. You can see the cluster of it. Here cluster is less. So here pressure is less. So if the pressure is less on the structure, you can say it can sustain the conditions we have considered in the simulations. Similarly, here the velocity contour and the streamlines between the original and optimum fuselage. You can see. So here you can. It is very very near to the things, but I just compared it and just find out that the true flow acceleration enhances the aerodynamic efficiency by dating the optimized design. And here in the streamline, here between the horizon and optimum fuselage, a smoother and faster flow at the trailing edge, like this. So confirm the improved aerodynamic performance. So this is the final result I will show you. So this is the original and the optimum fuselage. So this is the upper surface and the lower surface. Like that, we just compare and find out that the CP variation plotted against non-dimensional length L star. Here L star just use 42.5 centimeter, and for both the top and bottom surfaces, here the non-dimensionless parameter, and using this approach, I just find out where the position of coefficient of pressure is more, like that. I just compared. So application will be here. As I in the introduction itself, I just told you that surveillance. If you are using for military applications, so it will be definitely used for surveillance for internal security and foreign threats, and utilization of missile threat with less cross sections and decoys to protect high valued military or civil structures or machinery. So the main thing military application will be used like this, and the civil applications here we can find out very interesting and very useful. Disaster assessment and management, victim search and rescue with thermal imaging detection system. So medical supply and mineral exploration where human can't be. So there we can use traffic monitoring, railway track repair and maintenance. Wildlife monitoring also we can use. For border patrol also we can use. And for scientific research on expedition to North and South Pole, we can use home security. So like this application we can use. And the scope for future work can be like this, that navigation studies on formation, motion tracking can be done, and the creation comparison of a module specific wind tunnel for testing of photographing. So all this aspect is very and these are my applications references. Thank you. If any questions, you can ask.
Thank you, Dr. Bhushan Devangan, for your insightful presentation. Thank you very much. So it was a very nice presentation that you represented how the research hierarchy you have achieved, and you have shown, like, starting from the introduction, then you have discussed about the kinematics. Correct me if I'm wrong. If you have
Yes,
discussed the
kinematic
kinematics,
dynamics.
then you have gone for the dynamics. Very smoothly, you have moved from kinematics to the dynamics region. We have also shown the aerodynamic analysis of the bio-inspired flapping wing mechanism. Now I throw this forum open for any question. If anybody has got any questions, our expert is there to answer it. If anybody has got any questions.
Will I get the question in chat?
Anyone? Yes, they are open for putting up there any question in the chat box also. Okay. As any participants, any questions? No. Sir, I have only one question to you, right? How how important is that kinematic analysis to be done completed before the dynamics? You have started doing it giving it a very consistent and repetitive way. Like you have been telling us in the whole throughout the presentation that how you move from the kinematic analysis of the bio-inspired flapping wing mechanisms. Then you have moved from there to dynamic analysis, and you have completed an aerodynamic analysis also. That I have understood very clearly. So how important it was and you have also achieved an optimized fuselage design, right? So how important it was for you to first to go for the kinematic analysis, and then you have gone for the dynamic analysis. For us, we also want to understand the hierarchy of this your research.
It is a nice question. Thank you, Dr. Mukherjee. So basically, if you want to design anything, means if you are focusing on designing a mechanism. So designing a mechanism, we don't know how to connect different linkages with each other. Okay. So if you connect the linkage with each other, then you will just want to know whether this will have some kinematic issue or not. Means if I give some kind of orientation, whether another link which is connected to it, it will move or not. So it is our first approach should be there that we have to just focus how this will work. So initial step, it is like a baby step we have to take. First, we have to just focus on the kinematics, how this mechanism will work. If this mechanism is having a kinematic analysis can be studied and it is working properly, then only we can say we can just jump to the dynamic analysis. So like that only, I already discussed in this PPT that Newton-Euler equation I have just used to find out the different forces and power. So all these things are things connected to each other. If you are missing one thing, you can't jump to another. So like that, you have to just focus from the base, then you have to go up. You can take an example of the pyramid also. You can't just directly make the top of the pyramid. Okay, so for that, we have to just make a base, and with the passage of time, it will just make it to the top. So like that, I can just say.
Okay. Like in your first two slides, you have already mentioned like what are the categories of UAVs, like fixed wing, foldable flapping wing. Okay, sir. Actually, it's my question. Like, why? How do I measure what is my ability for any kind of UAV applications? Like these days, there are many hue and cry in the market that my UAV has to be getting a good range, or it has to deliver certain payload. So how do I choose? Like there are certain boundary conditions for me. So how do I choose that I develop a fixed wing aircraft or a foldable flapping wing, I can go for a foldable flapping wing mechanisms, or directly an UAV. So what will be the guiding conditions, or rather the boundary conditions for us for choosing what kind of design that we may follow?
Actually, Dr. Subo, it is a good question because whether I will say that it is your flow should be like that, it should be optimized. Means all thing you have to just consider, means battery weight, mechanism, what kind of mechanism and what kind of function you have to want. So all these things you have to just find out. Then only you can just say which UAV will be suitable for your function. So before that, you must understand what is your requirement. If you want to have some long range, then you should go for that what I say fixed wing, because the fixed wing is very developed right now as compared to flapping foldable wing. But it is also a research, so you can just take the fixed wing, because if it is a very urgent, so you can focus on that fixed wing UAV, and you have to optimize your requirement. Means in trade-off you have to do. It is not like that you can get everything.
Yes, yes.
It will be some limitation in the range and some battery strength, and will be the weights will be some constraint. So like that, you have to just focus on it. And if you considered and taken all the trade-offs, then you will come to the conclusion, and you will find out that this type of UAV wing is sufficient for me.
Yes, sir. Yes. Thank you for all your insights. And I once again take this opportunity to thank you for joining us from CMERI Durgapur. Yes, sir. Thank you. Sir, I will just engage now Surajit, sir. Sir, am I audible? Sir, if you can just go on with your vote of thanks. Surajit, sir, am I audible? Bhushan, sir, please just hold on. I'm calling
Okay.
Surajit, sir.
Okay.
Yes,
So
Surajit sir is here for sharing vote of thanks.
thank you very much. Although it was very attractive, your lecture, and you have covered all the possible points of related to your subject matter. And anyway, the number of participants were not so much high. Maybe it's a working hours, so maybe some people they're busy with their busy schedule. But I hope that, by the way, this program is already there in YouTube. It is a live streaming, and live program is already going on. So hopefully, a lot of people they have already seen. Some students they are also watching. So at the last, this is my duty to give the propose the vote of thanks. So I would like to thank the panelist from Dr. Bhushan from CMERI Durgapur, and also Dr. Mukherjee, who is the moderator of this entire program from the Institute of Engineering and Management Mechanical Department. And I hope that you have enjoyed our panelist. He has enjoyed in participating in our program, the Institute of Engineers program from the student chapter. And I hope we will get lot of good feedback from various corner, from various attendees who are there from outside Bengal also. And this way, thank you very much and wish you all the best. Thank you and Jai Hind.
Jai Hind.
Thank you, sir. Dr. Bhushan Diwangan, I would like to thank you again from the Institute of Engineering and Management for joining us, and also Dr. Surajit sir for giving us this opportunity to arrange this webinar. One thing is definitely we have very less participants today, but yes, our classes has not yet started, so it can be said that students are not yet joined here. But yes, we are in collaboration with IEI. We have been conducting in many webinars all the year round. So we'll have you again for us in joining us. So in a different subject. Thank you again, sir. Thank you again, Dr. Surajit sir. Thank you, Bhushan Diwangan sir, for joining us. This is from Institute of, on behalf of Mechanical Engineering Department, Institute of Engineering and Management. I would like to thank you for this very, very good presentation. And we had a clear idea about what the bio-inspired foldable flapping wing mechanisms can deliver to us, and what new is going on, how the design process is being, you have been make us understand very well. So thank you again, sir. Sir, we can leave now.
Okay.
Yeah. Thank you.
Okay. Thank you.
Thank you
sir.
very much.